Hi guys, me and my team want to explain to you about underground utility for survey and mapping. Let me explain what is introduction for underground utility. Underground utility is a process of identify the position and leveling public utility means which are located underground. Second, underground utilities refer to the detection, positioning, and identification of bird pipe and cable beneath the bottom. Third, the determination of position is often obtained with conventional and modern survey equipment. The detection and identification of underground utility requires special tools and technique. Fourth, principally, underground utility mapping is the combination and marriage between two major fields of the data, namely geographic and geometric. What is definition for underground utility? Underground utility mapping is a technique used to detect and georeference underground structure, including water pipelines, telecommunication cable, gas pipeline. For a construction project, underground utility survey can be used to produce georeference as built plan, which in turn are used to establish a comprehensive assessment of below ground space usage. Mapping using the data collected from a underground utility survey reduce project planning time as well as minimize the risk of costly adjustment to be the design or mistake further down the line. Objective. First, main objective is to act as a repository of reliable and accurate underground utility data comprising power and telecommunication cable, gas, water, and sewerage pipe provided by the utility agents in a systematic geographic information system approach. Second, explanation on how to choose of locate signal or frequency or grounding technique can create boundary distorted field that interfere with your ability to accurately map out your bounded utility. Third, make JUPEM a center of excellence and reference in the field of cadastral survey, mapping, geodetic, underground utility mapping, and geospatial information. Theory and concept for underground utility is combination this knowledge with expertise in using the latest technology, including ground penetrating radar equipment, and know how to overcome any limitation to ensure client receive true details and accurate result. Second, technique use the latest technology with expert method to explore detectable feature underground with a suite of technology including ground penetrating radar and electromagnetic locator. We can analyze reflected signal from structure, surface, boundary object, and layer beneath the ground. Third, ground penetrating radar use radio wave to non-destructively locate object and subsurface structure in materials like soil, rock, concrete, asphalt, wood, and water, sensor and software.
Next, I will present you about instrument, hardware and software. First instrument can be used is ground penetrating radar or GPR. The most often misstated description we hear when people call US for a utility locating survey is to ask for a ground penetrating radar survey or GPR survey or simply a radar survey. These descriptions are misstated about there is an incorrect assumption that ground penetrating radar is all that need to successfully find out utilities. However, GPR cannot be guaranteed to do that. Next instrument is electromagnetic or radio frequency technology. Electromagnetic locators are designed specially for finding underground utilities made from metals such as steel, iron, gas and water pipe, and electric and communication cable. Next instrument is cable avoidance technology or CAT. The name of instrument cable avoidance is a little misleading because as well as being a very capable cable wire locator. It is also extremely effective at detecting metal pipe too. Next is radio frequency or RF. RF pipe and cable locator are a useful tool in locating utilities line. The operator uses the transmitter component to impress a signal on a selected utilities line. This can be accomplished through a variety of methods, directly connection, a clamp around the utility, or by induction. The receiver is looking for the signal pressed on the utility. In underground utility, we can use three software. First is the Great HD3 software. This software, the highest resolution post processing. Great HD3 software is developed by IDS in Italy and is dedicated to viewing GPR data using powerful 2D and 3D processing algorithms. This software can integrate capture information with GPS or total station, the result being compatible with CAD and GIS system. Next software is GPR Soft TM software. GPR Soft TM is the affordable and user-friendly solution for displaying, post-processing and interpreting ground penetrating radar data with an intuitive interface and the shortest possible learning curve is allow you to focus on your work rather than on the tool you are using. GPR software has a full support for data file from all the major GPR manufacturers. As software can be used in underground utilities in survey and mapping is Geopointer at software. Geopointer at is a GPR post-processing software that combines GPS coordinate positioning on the map, image and much more from a geophysical study in single system. It's an easy way to document investigation area. Geopointer X brings a new possibility in the way geophysical data in analyze not only data in the geophysical tool is available, but also an entire set of data about the location of the survey can be viewed. They have three types of data. First is data product. Second, data owner. Third is data user. This picture show the workflow of underground utility mapping.
One method that is used in underground utility surveys is pipe and cable locator survey. Utility survey or mapping is aimed at finding and identifying all underground facilities within the sites to be investigated. The pipe and cable locators have been used for more than 2 decades to locate underground utilities. It applies the theory of electromagnetic induction to a metallic target line, and consequently an alternating current is generated. Then the signal is transmitted to a receiver, facilitating the location of the signal center to be identified. With advances in technology, it is now possible for a well-trained operator to locate the depth of the induced line with good precision. Electromagnetic induction. A pipes and cable locator does not find buried pipes or cable. It detects a magnetic field generated by an alternating current along the line. This magnetic field shapes along the line a cylindrical shape and is known as the signal. However, it is not possible to insulate against the flow of electricity against a magnetic field, and the shape of this field is not altered by cable insulation or by the presence of different types of soil. Alternating currents create the detectable magnetic field or signal because it provides not only a field but also an oscillating frequency of reversals in such a generation that makes it possible to position effectively by means of the principle of electromagnetic induction. For a current to pass, an electric circuit must be completed. The detectability of current flow in a properly insulated buried conductor shall be influenced by the low-powered signal source at the surface. The available voltages shall be unable to pass through isolation, and capability at AC circuits shall also have an effect on current flow detectability. Magnetic pipe and cable locators operate because of the magnetic fields that are present under the surface of the Earth. Metal objects below the surface of the Earth are influenced by magnetic fields and can thus be detected using magnetic locators. A shunted locator should be able to detect the presence of a metallic object when the attraction of the two magnetic fields on the sensor is different. The locator alerts the consumer with a high-pitched sound and a visual indicator that a metallic object is present. Signal frequency. High-frequency signal would appear to be more effective than low-frequency signals. However, since a high-frequency signal flows more easily to the ground through capacitance, it does not hold as much as the same intensity of a low-frequency signal. Another disadvantage of high frequencies is the ease with which signals that are aimed along the target line can couple to other nearby lines by mutual induction. This often makes tracing of a target pipe or cable in a congested area more difficult. A large pipe or cable diameter increases the surface area of the line, which is in contact with the ground, so the signal leaks to ground. The same signal strength leaks away over a much shorter distance from a large pipe than a small one. The ability of the ground to pass current varies locally. Wet soil is a stronger conductor than dry sands, and the resulting impact on capacitance can vary the apparent conductor conductivity. The effect of high ground conductivity is to make it easier to induce current flow, and therefore, due to the good return path a signal in a buried conductor is. Conversely, low ground conductivity requires more energy to induce a signal onto a line, but it will then be detectable along a greater length of the conductor. Locating a sound. Although it is an AC signal, the magnetic field of signal produced by a sound is different to the signal produced by the signal transmitted. The sound produces a field distribution which, as with a grid, is not cylindrical but sausage shaped along the aerial core orientation. As a sound is approached with a horizontal aerial, it will detect a rising signal as it comes within range. That will then fall to null again, giving the illusion that the peak signal has been passed over the sound. But if the traverse continues, the signal will rise to a much higher point again, the height of which shows the sound's real and exact location. It will then fall to null again, followed by a small rise and then fade away. A vertical aerial produces a single null reaction over the sound, but this null reaction is present at right angles to the sound along an axis. For this reason, it is not appropriate to use a vertical aerial to locate a sound. Planning of work. Staff entering manholes will have been trained and have been awarded the certificate for confined space works. Due to the nature of works, manhole entry is not recommended for utility surveys, as information can be acquired by sound, and in case of unable to survey due to slip or flow or any other dangerous possibilities, photographs will be taken for record purpose. When working on the carriageways, temporary traffic arrangements will be coordinated in accordance with the Code of Practice for signing and guarding as issued by the Highways Department. PPE such as safety helmet, harness, shoes, and goggles will always be provided. Staff will take necessary precautions and utilize them when potential hazards are identified. An emergency telephone list will be provided for the team leader to make sure that the utility companies, police department, and fire department can be contacted should the need arise. Systematic planning will be undertaken for the commencement of the contract. A preliminary schedule will be arranged in accordance with the agreement signed between the contractor and the client. An exhaustive search of the available utility maps will be completed in order to get an understanding of the potential layout of subsurface utilities. A report team will be established who have a good understanding with reference to the requirements set out in the contract signed with the client. This is facilitated by the use of a total station and arbitrary control points, where possible manholes, valve, vaults, chambers will be opened in order to map their extent and depth.
Now, process of works of underground utilities for survey and mapping. The first step of survey and mapping of underground facilities is to determine the actual property owner. This is due to the reason that permission with written evidence is needed to enter any property. The second step is to identify the existing utilities buried underground. This step is very important because there may be some underground utilities that are never documented. This process needed to be done without digging into the lower ground layer. Fortunately, there is a subsurface geophysical equipment that can be used, which is the ground penetrating radar (GPR). One of the advantages of GPR is that this equipment can detect non-metal targets without using tracer wire. The higher the frequency of the signal, the higher the ability of GPR to detect smaller objects or detect the smaller distance between objects. To obtain 3D information, the radar antennas must be moved along the ground. The data is recorded quasi-continuously. To penetrating waves, the data is analyzed. The third step is to map the underground utilities. Next, process of data. After the survey of underground utilities has been carried out, the data obtained must be used to create a map. There is some software that can do data analysis, post-processing, and modeling to obtain graphical product representation. The first step of post-processing is to perform temporal filtering. This step is to reduce low produced from the large energy input from the air wave, ground wave, and near-surface reflectors. The second step is to determine the time gain for the data sets. Time gain is a non-linear process. Thirdly, spiking deconvolution is done to improve data resolution. After that, temporal and spatial filtering is performed. Temporal filtering can be defined as the filtering that is applied on the dataset according to long the time exists. Temporal filtering includes bandpass filtering in order to achieve bandwidths that are about equal to the center frequency. Next, velocity semblance analysis is performed. Elevation and velocity static corrections must be performed to get subsurface images that are realistic. After that, by using the previous semblance velocities that have been obtained in the previous step, normal move-out is performed to regard the separation of transmitter or receiver to depict approximate zero offset rays. The last step is migration, where this step is performed based on velocity spectrum in order to put back the reflections to their respective correct spatial position. One of the examples of software used nowadays to post-process GPR data is GPRsoft. Next, output. The underground utility maps in Malaysia must follow the coordinate system that has been decided by JUPEM. The maps must be based on rectified skew automorphic RSO coordinate with reference to the geocentric datum of Malaysia 2000, GDM 2000 horizontal data. Even though the coordinates of the Cassini-Solner state plan coordinate systems, RSO Malaya which based in Kertau and RSO Borneo which based in Timbalai are already used for ground surveying. For underground surveying, these coordinates must be projected into RSO Malaya on GDM 2000. For Peninsular Malaysia, for Sabah and Sarawak. The map of underground utility in Malaysia must have appropriate metadata that differs to the Malaysian standard for geographic information. Other than that, the underground utility map should contain map legend, parcel boundaries, disclaimer, date and any marginal information.
Next is accuracy of location and survey for normal case. First is the position and level of locatable surface at the record point and interval not exceeding 1 meter should be related to the control survey station to better than. Second, the position and level should be related to the Hong Kong 1980 geodetic datum and should normally be related to the center line of pipe, duct or cable, and invert of sewer and drains. Third is any no underground service of information which cannot be surveyed to the occurrence state above, other than by excavation, shall be entered in unique AutoCAD layer defined as unreadable. 4 is where full detail of underground survey cannot be determined without excavation. This detail shall be educated from the utilities undertake, record drawings and entire into the drawing in a unique AutoCAD layer defined as record. And lastly, wherever access is available from the surface deep to the underground survey shall be checked as a means of calibrating the survey work. Position of assets measurement shall be not as attribute in the drawings.
Okay, last but not least is conclusion and recommendation. Underground utility survey and mapping. First is issue are regarding data quality, lack of skill and knowledge, and also the requirement of legislation on underground utility mapping are number of the challenge faced with regard to underground utility mapping in Malaysia. Various initiatives are being undertaken to overcome this challenge. This good practice of underground utility pipeline mapping in densely populated urban area with refinement of the utility data quality is hence needed for the expansion and upgrading of utility pipeline and to ensure the sustainability of the urban underground surface by means of accurate utility pipeline mapping and excavation in the future. Third, securing precise utility data is also one of the basic needs of the 3D underground cadastral database toward achieving the development of digital Earth.